we go.
Yeah.
All right, let me just test it to see if. Okay. All right. Good afternoon. My name is Tommy Dacanay, and today I'll be presenting on my master's thesis research on ultra-high performance concrete shear walls in tall buildings. To start, I'll go over the motivation for my research and the objectives of my thesis. Then I'll go over shear walls in tall buildings, followed by explaining exactly what ultra-high performance concrete is. Then I'll talk about the lattice discrete particle model, which we've used for our shear wall simulations. Then the UHPC shear wall parameter study, again using these simulations. Following that, a study of the sustainability of shear walls. Then lastly, I'll conclude and go over some future work that could come from this research. So let's get started. There are two projects involved with my work. The first is through the National Science Foundation, and the goal of this project is to deliver a validated computational modeling platform for analysis to collapse of UHPC members with the lattice discrete particle model, which I'll talk about more a little later on. And the second, which my research specifically is funded by, is through the Qatar National Research Fund, and the goal of this project is multi-objective design, meaning the satisfaction of structural constraints while also considering things like sustainability and architecture. The goals of my thesis are to assess the viability of using UHPC for shear walls in tall buildings, exploring the metrics of increased structural efficiency and improved sustainability, and in this process develop a framework for comparing UHPC structural solutions to other materials. So let's go over shear walls in tall buildings. First, I'd like to note that this research can certainly be applied worldwide, but this project is specifically geared towards tall buildings in Qatar. Doha is the capital of Qatar and is currently going through somewhat of a building boom, with 26 completed tall buildings defined as taller than 150 meters and 12 currently under construction. The average building age in Doha is only 4 years, and the most common building material here as well as worldwide is concrete. So the picture on the left shows the elevation of a typical lateral load resisting system. The picture in the middle shows for that same building the plan view, and on the right we see a lateral load resisting system of a different building under construction, and you can see the shear walls and link beams in this example. I've highlighted where this elevation view corresponds to on the plan view, in that middle section there. So in this section I've blown up the bottom portion of the lateral load resisting system, and you can see these shear walls highlighted in yellow connected by these link or coupling beams here. And the simulations, which you'll see later in this presentation, are meant to represent a portion of these shear walls highlighted in yellow. So I've been mentioning these shear walls, but how do you actually define a shear wall? ACI 318.14 defines a wall as a vertical element designed to resist axial or lateral loads, or both, with a horizontal length to thickness ratio of greater than 3, less than that it would be a column. And it also defines a structural wall as a wall proportioned to resist combinations of shears, moments, and axial forces in the plane of the wall, and says that a shear wall is a structural wall, kind of interchangeable in their definition. So shear walls resist lateral loads applied to the building due to earthquakes or due to wind, and also resist, especially in the case of tall buildings, gravity loads that are tributary to the member. Typical thicknesses of shear walls in tall buildings range anywhere from around 600 millimeters, which for this case is a 55-story office building, all the way up to 1,000 millimeters, which corresponds to the Kingdom Tower, which is currently under construction, and upon completion will be the tallest building worldwide. So in tall buildings, concrete shear walls are relatively thick so that they have the requisite shear capacity to have adequate seismic performance and stiffness to resist wind loads and meet serviceability requirements. So these shear walls require, of course, a lot of concrete as well as the other members in the building. And the manufacture of concrete results in significant effects to the environment because it involves energy-intensive materials like Portland cement. So how can we improve upon these issues? This research examines ultra-high-performance concrete as a potential solution by reducing the wall thickness and improving structural efficiency, and in that same process, using less material to obtain a more sustainable design. So what exactly is ultra-high-performance concrete? It's a relatively new class of concrete having been developed in recent decades, and it's characterized by increased compressive strength, tensile strength, improved ductility, durability, and fire resistance. And in this source gives the compressive strength for UHPC anywhere between 140 to 250 or more megapascals. And I'd like to note that all of these characteristics that I mentioned are very important to the performance of shear walls in tall buildings. So I mentioned that we want to improve these shear walls by making them thinner. How do we determine how much thinner these shear walls can be? To answer this question, we've used simulations using the lattice discrete particle model. The lattice discrete particle model has been developed by Dr. Gianluca Casadas at Northwestern University, and it simulates concrete as a two-phase material. The aggregate pieces simulated as spherical particles distributed randomly throughout the member, and a lattice connects these particles. A tessellation of this lattice results in polyhedral cells which contain the particle. You can see an example of that on the bottom left here. And these polyhedral cells represent the matrix in which concrete or aggregate particles are embedded in real concrete. The LDPM conveys benefits like the accurate modeling of the initiation and propagation of cracks in structural members or concrete structural members, and also gives us the ability to simulate discrete fibers embedded in the concrete matrix and their effect on post-peak ductility. These fibers are what gives UHPC its post-peak tensile capacity. And on the bottom left, you can see these fibers randomly distributed throughout the matrix as simulated by the LDPM. The right image shows the particles in a shear wall specimen randomly distributed throughout the matrix. And these particles have been blown up so you can see them better. They're 5 times their actual size. A number of LDPM parameters defines the behavior of a specific type of concrete. I've broken these into 2 groups. The first one describes the behavior of a specific type of concrete, and the second grouping, if fiber reinforcement is present, defines their effect on the behavior of the member during loading. The LDPM is embedded within a commercial software platform called Mars. This commercial software is installed on the supercomputing cluster called New River here at Virginia Tech, and this marriage of hardware and software resources lets us simulate large-scale concrete structural members, although we do need to be careful of the computational cost involved with the various sizes of these members. Mars gives us the benefits of completely customizable construction of our simulations, meaning that we can have any sort of geometry of the members and rebars and so on, and apply any sort of loading or restraint conditions that we want. And also gives us the ability to have interactive visualization of the results using ParaView, which is a separate freely available program. This image shows one of the capabilities of using the LDPM and Mars. We've simulated all the reinforcing bars for an experimental shear wall specimen. So it goes to show you that you can simulate the exact reinforcing bars and all the other aspects of tests. So now with the LDPM and Mars, all the resources that I've talked about, we've taken that and performed a parameter study on UHPC shear walls. I've compared two cementitious-based composites. The first, a UHPC called CoreTough, has a simulated compressive strength of 231 megapascals, and the second, an HPC, has a simulated compressive strength of 51.7 megapascals. You can see the material proportions for CoreTough on the bottom left here, and some information about the material composition for the UHPC and HPC on the right. The specific shear wall specimen that has been modeled here has a length of 300 millimeters and a height of 400 millimeters, giving an aspect ratio of 1.33. The slenderness ratio of the shear wall, which changes throughout these simulations, and you'll see those on the following slides, is calculated as the height of the shear wall over the thickness. I'd like to note that the curves which we'll be seeing are presented as drift ratio versus base shear, and the drift ratio is calculated as the displacement at the top of the wall divided by the wall height. The dimensions chosen here correspond to approximately a 1/10 scale of an actual shear wall in a tall building. According to a UT Austin report, direct models of concrete structural members are usually constructed at 1/5 to 1/10 scale. Smaller than 1/10, it's been said to can be unreliable. So due to the effect of increased computational cost at larger scales, we've chosen 1/10 scale as a good compromise. I'd like to note again that no full-scale validation was performed for these simulations that you'll be seeing due to the lack of available shear wall experimental tests with adequate material characterization data. Here are the restraint and loading conditions on the shear wall specimen. So the part outlined in black here is simulated by the lattice discrete particle model, and there's a elastic concrete block at the bottom and the top of this section outlined in blue and red. On the bottom face of the bottom elastic concrete block, there's a fixed condition applied. It can't rotate or displace in any direction, and everything else is free. At the top of the top elastic concrete block, there's an applied distributed axial load. And on the side face of the top elastic concrete block, we've applied a velocity curve to provide the lateral loading on the specimen. And due to the application of a velocity curve, this test is displacement controlled as opposed to load controlled. So here we've studied the effect of varied axial stresses on the specimen. So during this test, the axial stress is constant, as it is in every other simulation that you'll be seeing. It ranges from 9% of the compressive strength of the concrete to all the way up to 54%. You can see in these two bottom simulations, we have an initial elastic portion followed by a nonlinearity, and those continue on. The third one is a bit different, and we'll see why in a second. So we can see here that the nonlinearity in these two curves are due to the development of a horizontal flexural crack at the bottom of the wall, as shown here. And as the test goes on, this crack develops further, and the wall simply starts to tip over with the continued application of lateral load. You can see a similar effect in the specimen with the highest axial load. There's the development of this flexural crack at the bottom of the wall, and also some compression cracking on the right side. The main difference is you can see this big drop is due to the development of a diagonal shear crack in the wall. And this crack opens further as the test goes on. So I'll explain why in a second, but we've added vertical steel reinforcing bars at the wall edges. We do this to control the opening of that flexural crack which you saw, and allow the wall to reach a lateral load that's required to develop this diagonal shear cracking, which you saw in the specimen with the highest axial load before. There's a perfect bond between the concrete and the rebar, meaning that no bond slip law was applied. So I'd like to go over why we've added these rebars in the way that we've done this. So again, we're applying this lateral load at the top of the wall, and this creates a moment on the wall. You can see the stress distribution due to this moment, my over I, and there's a side in tension and a side in compression. This side in tension is the reason why that crack develops and propagates in the wall. And that's why we've added these reinforcing bars here to control this cracking and allow the wall to reach that diagonal cracking failure mode. So you can see the effect of that in these two images. On the left, we have a specimen without rebar, and on the right, we have a specimen with rebar. You can see in the rebar specimen that this horizontal flexural cracking is controlled, and the wall is able to reach this diagonal shear cracking failure mode. So now we're studying the effect of microsteel fiber reinforcement on the structural response of the shear wall. So you can see there's one example without fibers and another example with fiber reinforcement. The fiber reinforcement has no effect on the initial stiffness of the wall, as you can see here, but does have the effect of increased post-cracking load capacity. These images show the cracking in the two walls at equal drift ratios. We can see that in the specimen with fibers, the crack opening is less than in the specimen without fibers. So one effect of this increased post-cracking load capacity is increased dissipated energy. Dissipated energy is critical to the performance of shear walls in seismic events. And in this case, dissipated energy is calculated by taking the area underneath the base shear lateral displacement curve. One thing you'll note is in all cases, the dissipated energy increases with the addition of fiber reinforcement, but with increasing axial stresses, the dissipated energy actually increases more. This is hypothesized to be due to the effect of confinement. So with crack opening, the fibers bridge the cracks, and as they open further, they're pulled out. Confinement on these fibers increases the work during fiber pullout, and in turn increases the dissipated energy during lateral loading of the wall. Here we're comparing directly UHPC and HPC shear walls with equal slenderness ratios and equal applied axial stresses. You can see this bottom curve is for an HPC shear wall, and the top two curves correspond to UHPC with and without fibers. The initial stiffness of the UHPC shear wall is 47% higher than that of the HPC shear wall. This increase is the same as the increase in the modulus of elasticity of the two materials. At a drift ratio of 1%, which means the wall has already begun cracking, the UHPC shear wall has over 3 times the lateral load capacity as the HPC shear wall. So now, taking the information we've learned in the previous sections, we're studying exactly how thin we can make these UHPC shear walls with equal or better structural response. In this case, we're increasing the slenderness ratio, the same as decreasing the wall thickness, two names for the same thing, until it has equal stiffness to the UHPC or to the HPC shear wall. Excuse me. As we decrease this thickness, we keep the axial load constant. And the way we can think of this is we take a building with an HPC shear wall, and we want to take it out and swap it for a UHPC shear wall. So none of the loading conditions are changed between these two scenarios. So we need to keep the axial load constant on the shear wall, not the axial stress, as this changes with changing thickness. So you'll see the results in a second, but we've determined that we can increase the slenderness ratio from HPC to UHPC by 71%, or in other words, we can decrease the thickness by 42%. And again, the walls have equal stiffness and therefore equal performance under wind loading, as elastic stiffness is what determines the performance under wind loading for shear walls. And the UHPC shear wall has greater post-cracking structural response even with the decreased thickness and energy dissipation, and therefore has superior seismic performance. So here you're seeing the results of this thickness study. The UHPC examples, which are the top two curves, have this increased slenderness or reduced wall thickness. This bottom curve and the middle curve are for HPC and UHPC with equal axial loads. We've also tested this extra top green curve, which corresponds to an increased axial load on the UHPC. What this indicates is the effects of any sort of slenderness are not seen here, so we can apply a greater axial load onto the UHPC shear wall with no ill effect. It actually has a higher post-cracking load in this case. So again, we can see that the HPC and UHPC walls have equal pre-cracking stiffness, and after cracking, the UHPC shear walls have higher loads, over 3 times the lateral load capacity. So I'd like for you to take a look at the cracking in the walls at equal drift ratios, in this case 1%. This is for the HPC section. You can see all the diagonal cracking that's developed in this specimen. For the UHPC specimen with equal axial load, and for the UHPC section with the greatest amount of axial load. And we can see some changes in the inclination of these cracks due to the principal stress planes changing with this increased axial load. Let me back up and show that effect again. So I'd like to show the crack propagation during the simulation so you can get an idea of how that occurs. On the left we have an HPC section, on the right UHPC with fibers at equal axial loads. So as I've shown before, we've calculated the energy dissipation as the test goes on for all these sections. And again, we reached the conclusion that UHPC has a higher dissipated energy even with that decreased wall thickness, and higher still with the addition of fibers, and the increase in axial load results in an increase in the dissipated energy, again due to the effects of confinement. So to recap the results of the parameter study, increased axial stress generally results in a higher maximum shear capacity, and I say generally because at a certain amount of axial load the effects of slenderness will take hold and could decrease the shear capacity of the wall. Steel fiber reinforcement has no effect on the initial stiffness of the shear wall, but does increase the post-cracking capacity and therefore energy dissipation of the wall. And in this particular study, a UHPC shear wall has equal uncracked stiffness and superior post-cracking response at a thickness 58% that of an HPC shear wall. So given this conclusion in the reduction in wall thickness possible using UHPC, is the UHPC solution actually more sustainable than the HPC solution? And that's what we're studying here. So to answer this question, we've used a life cycle assessment approach. UHPC, again, presents advanced properties that can be advantageous for using in structures, but it does so at the cost of using energy-intensive materials like Portland cement and microsteel fibers. So we've used SEMA-Pro to answer the question of sustainability to perform life cycle assessments for these shear walls. And I'd like to give a special thanks to Dr. Sean McGinnis at this point, who helped me build my model for in SEMA-Pro for UHPC shear walls. The LCA has been performed for both Qatar and the United States in this study. So for a brief overview of how a material is defined in SEMA-Pro, we break up the concrete into its constituents. It's tough to read here due to the resolution, but this is cement here, microsteel fibers, superplasticizer, and so on. And each one of these nodes, which you see here, corresponds to a process involved in the manufacture of the materials, on down from the extraction of raw materials to higher level processes like the manufacture of pig iron, and up to processes like hot rolling steel. So after we've defined the network diagram for a material, we use LCA methods to get our results. There are many to choose from. The two chosen here were Recipe 2008, which is a widely accepted, both scientifically and politically, LCA method, which takes a multi-issue approach, meaning it breaks up the results into categories such as global warming potential and ecotoxicity and so on, and then uses certain factors to combine these results into a single score. The reason we want a single score is so we can compare different materials to each other and be able to say which one is more sustainable. The second method chosen is called cumulative energy demand, and this is a much simpler method which does not break out these results into different categories. It simply calculates the embodied energy of all the processes and combines them. I mentioned that this study has been performed for both Qatar and the United States. This is done using the information available, which in this case is the electricity mixes for each country. You can see the electricity mix for the United States is dominated by hard coal, natural gas, nuclear, hydropower, and then a mix of other ones in smaller amounts. And Qatar is fairly easy. It's a very rich country in terms of natural gas, so currently 100% of its electricity generation capacity is through natural gas. Here I've shown the constituent single score results. So the constituents include coarse aggregate, Portland cement, and so on. And what I'd like you to take out of this is that, again, I've broken up the results into those from Qatar and the United States, but they're not actually that much different from each other. There's not a significant difference in the sustainability from manufacturing in these different locations. So from here on out, I'll be showing the results for just one country. They're not all that different from each other. So this chart shows the single score results for sustainability for each constituent. We can see that for a given mass of constituent, the superplasticizer has the highest environmental impact. But as you'll see in the following slides, it's used in much smaller quantities as compared to the other constituents. So it'll end up having a fairly small environmental impact. Here are the mixed designs for UHPC with and without fibers and HPC. And we can see that the amount of Portland cement differs between these two types of concrete. I've highlighted the top two entries. As you'll see in the next slide, they contribute the most to the environmental impact of the shear walls. Here are the life cycle assessment results for a unit volume of UHPC with fibers, and we can see here that the environmental impact of the material for a unit volume, again, is dominated by the Portland cement and the microsteel fibers. This table shows the single score per unit volume of UHPC and HPC. The second line normalizes this to the HPC, and in this process we can see that the environmental impact of UHPC without fibers is around 1.9 times that of HPC, and with fibers 2.5 times that of HPC for unit volume of each. So the numbers on the bottom are showing what this means for the shear walls. The original thickness of the shear walls is 60 millimeters, and we've found that we could reduce that to 35 millimeters while maintaining the same initial stiffness. These break-even thicknesses with and without fibers shown below correspond to this 60 millimeter value divided by these numbers here. So that's the necessary thickness we would have to reduce the walls to have equal sustainability. We can see that we didn't quite get there, and I'll talk more about that in the next slide. So this shows the sustainability results for the shear walls themselves, which take into account the volume of concrete used in each shear wall. We can see that through this normalization, the UHPC shear walls without fibers have 6 to 10% greater environmental impact than the HPC shear walls. With fibers, that number is 47 to 58% greater environmental impact than the HPC shear wall. I would like to put a note on these results, as there are several aspects that haven't been studied in this research that could change these results. One is the potential longer lifespan of the UHPC shear wall because it has higher durability and also better seismic performance. So the UHPC shear wall, if it was in a very corrosive environment, might last significantly longer than the HPC shear wall, and that would significantly affect these sustainability results here. Another effect is the reduction or elimination of some or all of the horizontal and vertical bar reinforcement, which lowers the amount of steel used and improves constructability. This last bullet is related to the second one in that with the reduction or elimination of steel bar reinforcement, we can reduce the amount of formwork required and construction can speed up. This can also have an effect on the sustainability of the shear wall when looking at a big picture. Finally, I'd like to compare the structural dissipated energy and embodied energy, which is related to the sustainability of the shear walls. We can see that I've presented a ratio of dissipated energy to embodied energy, and in all these tests, they're around 2 to 3%. The UHPC shear wall without fiber reinforcement has the highest ratio here. So what this is showing is how much energy we get out of the wall when it's loaded laterally and energy is dissipated in the process, as compared to the amount of energy which it takes to actually manufacture all these materials and assemble the wall, which is the embodied energy. This result can potentially be improved through topology optimization. A topology optimization seeks to find an optimal geometry of a member given a set of loading and restraint conditions, and also geometric restraints, like we can only put material in these certain areas. Structural and sustainability from this study can be input into the topology optimization protocol for the design of shear walls in tall buildings. Some of the parameters that could come from this and be inputted into topology optimization protocols include embodied energy per unit volume of concrete, embodied energy per unit weight of concrete constituents if we wish to make the mixed designs customizable, material properties of the concrete including modulus of elasticity, so we can determine the stiffness and if that's okay for our solution, compressive strength, and so on. And lastly, energy dissipation per unit volume of concrete, which of course depends on the aspect ratio of the wall, principal stresses, expected drift ratios during seismic events, and so on. And this work is currently underway with the QNRF partners to Virginia Tech, which include Johns Hopkins University, the University of Qatar, and Optimum Design Incorporated. So to conclude, with current technology, UHPC shear walls can be made significantly thinner, in this case a little bit over half as thick as HPC shear walls while maintaining equal stiffness. UHPC shear walls have at this thickness superior energy dissipation and post-cracking capacity, which results in better performance in earthquakes. And although using UHPC results in a slight to moderate increase in the environmental impact of the shear walls, the breakup of the constituent results show that reducing the amount of Portland cement used or microsteel fibers used would be very effective in improving this aspect of UHPC. Additionally to the sustainability results, potential improvements haven't been taken into account here, which include potential longer lifespan, reduction of steel reinforcement to improve constructability. In a more general sense, it's concluded that structural simulation using the LDPM and MARS can be used in place of experimental tests so that we can obtain results in a shorter time period with less complexity and with greater breadth of our study. And the relative sustainability of structural solutions can be compared using an LCA approach with the CIMAPRO software. So for some future work that could come from this research, larger scale or full scale simulations could be performed with realistic reinforcing bars as modeling techniques, software, and hardware improve. Validation of our simulation results here could be performed using experimental shear wall tests as they become available. Development of UHPC design guidelines could take place using simulation-based work. UHPC properties and sustainability results could be input into topology optimization protocols for the design of shear walls in tall buildings and other structural members. And the exploration of other UHPC structural solutions, not just shear walls, but anything like beams or columns, can use the structural and environmental framework developed here. Here are my acknowledgments for my research, my references, and I'll take questions now.